All right. Problem number 24, chapter 6 in your textbook. And let's start. So this problem is about an object, a block maybe, or a mass on a surface. So let's draw the free body diagram. First step, always. Always. Raise your hand if you don't do this as a first step always. Oh, well, put your hand down and draw the free body diagram instead. Okay, we got a push force. I call it F, and it's acting at some angle to the horizontal, below the horizontal. And notice I drew the components dashed lines because technically you're not supposed to draw components on a free body diagram. You would do that in a second diagram, but I'm going to do it on here just because I only have 15 minutes and I want to just kind of get through it. I promise I won't do it again. So we get the F push force at an angle. We got weight. We have a normal force because this is resting on a surface. And we have the friction. Oops. The friction going back. Cool. So we have almost 100% correct free body diagram. And when I say that, I mean it's not correct because of the components, but otherwise everything's correct. Now the next step, always, is net force equations. In this case, since one of the forces is not perpendicular or parallel, in other words, at some random non-perpendicular or parallel angle to another force, then we're going to have to break one of those up into components, and that's going to require two net force equations, one in the vertical and one in the horizontal. Before we do that though, let me just resketch the graph that you see in your book. This y-axis is acceleration, the x-axis is mu k, goes a little something like that. This is not curvy. And at 0 or mu k or frictionless, on a frictionless surface, the acceleration would be 3 meters per second. At 0 acceleration, mu k is going to be 0.2. And at -3 acceleration, meters per second squared, roughly, our mu k is 0.4. Cool. So we'll use this a little bit later after we write after we write our net force equations. So we're going to need a net force equation in the x direction and the y direction. Let's just start with the y because I kind of feel like it. In the y direction we have three forces, Fn up, Fg down, and Fy down. If we call up positive, then we got Fnet equals Fn, positive Fn because it's up, minus Fg because it's down, minus Fy because it's down. And we know that this block is not accelerating up or down, it's staying on the surface. So the net acceleration in the y direction is 0. So Fnet is 0. Huh. Oh, strange. Anyway, and then what we can do is we can bring the two negative terms over to this side and get a nice expression for the normal force, which we're going to need because we have friction up here. And we could even take it one step farther and substitute in what we know for these. We know Fg is mg, and we know that Fy is the opposite component of F, so it's sine. So this is F sine theta. Cool. What about the x direction? Excuse me. F net equals what? Well, we got two forces in the x direction. fx to the right, ff to the left. Let's call to the right positive. Pretty good. Now we can't assume that this is not accelerating in the x direction. Our push force very well could be large enough to cause this thing to accelerate. It could be small enough to cause friction to win and cause it to slow down. Or it could be just the right size so that ff and fx are equal and it doesn't accelerate. But we can't assume that. So we'll call it m a net, and fx is just the adjacent component, so that's going to be f cosine theta. Friction we can rewrite as mu k Fn. And oh, how convenient. We have an Fn term over here so that we can just plug that into here. And this becomes m a net equals f cosine theta minus mu k g plus f sine theta. So far so good. Now we can't really take this any farther, I don't think. No. So what we're going to do is we're going to now plug in values we know from the graph and try to shrink this down so that we can have everything given except theta. So I'm going to copy these two onto the next page, and you don't need to see me do that. It's going to take a few seconds, so I'm back. Alright, so I copied the graph and the x direction net force equation, which by the way is really a combination now of x and y, because we get the Fn term from the y direction. So Fy is embedded in here, believe it or not. So let's start plugging points in here. Well, we got at 0 mu, in other words, at a frictionless surface, our acceleration is 3 meters per second. So let's plug that in. So m times a is 3 over here. I'm going to leave it unitless. That's going to equal f cosine theta minus 0. Mu k is 0, so this term actually goes bye-bye. And that's our equation. So this is the equation at this point. What about this point? Well, that's not too bad either, because a is now 0, so this term vanishes. 0 equals f cosine theta minus, and at that 0, mu is 0.2. And we could do this third one too, but if you're keen, you'll see that you don't need that piece of information. 2 points is really all we need. And I'll show you how in a sec. We have mass and force here. Here we have mass, force, and angle. And we have angle in all of these. So typically you would say, well, 3 unknowns, you need 3 equations, you get this third equation. But, and there's nothing wrong with that, you can find that third equation and take a little longer. But if you see the following, it's kind of cool. Solve this for m. Take this m, plug it into here, giving us 0 equals f cosine theta minus 0.2. M is f cosine theta over 3 times g, don't forget the g here, plus f sine theta. Since we have a 0 here, we can bring this negative term over to the other side and set these equal to each other. F cosine theta on this side equals positive 0.2 f cosine theta g over 3 f sine theta. So not only did we get rid of m by this substitution, but look, each term has an f in it. And algebraically, that means bye-bye f. So we have cosine theta equals 0.2 times g over 3 times cosine theta plus 0.2 times sine theta. Let's combine our cosine thetas, and I'm going to do that in a calculator real quick. This is cosine theta times 1, and this is cosine theta times 0.2 g over 3. So if I subtract this cosine theta over, that's going to be really 1, 1, 1. Hold on. 1 minus 0.2 times g, which is 9.8, divided by 3. So 0.34, whoops, where is that? 0.347 cosine theta equals 0.2 sine theta. Divide 0.347 by 0.2, what do we get? 1.733. Sine divided by cosine is tangent. Whoa, how nice is that? So theta equals inverse tangent of 1.733, which equals second tan, oops, second tan, second answer, 60 degrees. And that's the answer. So we're pushing this, come on, pushing this block down at an angle of 60 degrees in order for this graph to uh, describe the motion of this object. Alright, next problem coming up soon. See ya.